So I believe it was in our last video that we looked at Euclid's Lemma, which was theorem. This was theorem 1.5. And it basically said if you have an integer that's neither 0 or plus or minus 1, p is prime if and only if p has this awesome property. If p divides a product, ab, then p divides one of the factors, a, or p divides b. That's a characterization of a prime p. So we want to follow up. We want to do an exercise. This is exercise 10 from our book, page 23. So exercise 10 from page 23 is from 1.3 section. It says, let p be an integer, p not be 0, and p not be plus or minus 1. So here's another characterization of a prime p. So p is a prime if and only if for every integer a, every single integer a, the greatest common divisor of a and p is 1, or p divides a. Okay, so let's prove this. This is an if and only if statement, so we want to prove this. In the background, we have p as an integer, so let's go ahead and declare that. Let p be an integer with p not 0, and p cannot be plus or minus 1. Okay, that's in the background. So I want to show if p is prime, then for every integer a, the GCD is between a and p is 1, or p divides a. So I'm going to start with the blue. It's called the forward direction. I'm going to assume the blue and try to get to the green. So let's suppose p is prime. And somehow I want to get to this green. I want to prove that for every integer a, the GCD of a and p is 1, or p divides a. So if I want to prove this for every integer a, I need to let a be an arbitrary integer. So I'm just going to let a be an integer. It can be any integer. Now, we can say that either p does not divide a, or p does divide a, right? P does not divide a, or p divides a. Which gives us basically two cases. So case 1, it would be when p does not divide a. So what happens if p does not divide a? Suppose the first case, p does not divide a. Now, we're going to let d be the GCD of a and p. Well, since d is the GCD of a and p, that means p divides a and d divides p, right? That's the first criteria of a GCD. GCD divides a, GCD divides p. But remember here that p is prime. So if I focus on the second situation here, d divides p. If p is prime, that means p can only be 1 or p, or d. Any divisor of a prime is plus or minus 1 or plus or minus p. But we're not thinking about negatives. We're not thinking about negatives because GCDs are only positive. So I'll say since p is prime, then d must be 1 or d must be p. Right? The only divisors of a prime that are positive are 1 and p. Now, is it possible for d to be equal to p? Is it possible for d to be equal to p? No, it's not possible. Note, d is not equal to p. Why can d not be p? Why? Well, we know d divides a back here, right? So if d equals p, then we would have p divides a. which would contradict that P doesn't divide A, which that P doesn't divide A. Okay, so that means D cannot be P. So what does that leave the only option for? D must be 1. Thus, D must be 1. That is, remember what D is, it's the GCD of A and P. Thus the GCD of A and P equals 1. Okay, so that gives us one of the either situations. Let's do a case 2. Case 2 is, so this was case 1 here that I checked. Now let's do case 2, that's the double check. What if P divides A? Okay, suppose P divides A. Well, isn't that exactly what we want to show for the second thing? So the second thing for the OR case is P divides A, so we're done. Then there is nothing to show. So remember, we were supposed to get an either or statement. Either the GCD of A and P is 1, or P divides A, and we have that. Okay, so that's the forward direction. So the backwards direction I'm going to do with a green arrow going backwards. So you want to assume the green, and you want to get to the blue. So let's suppose for each integer A, the GCD of A and P is 1, or P divides A. Okay, so we're assuming the green. We want to get to the blue. We want to get to this blue that I'm circling here. P is prime. Now the way I'm going to get to the blue is by using the Euclid Lemma version of a prime. So we will show P is prime by Euclid's Lemma. And remember what Euclid's Lemma says. P is prime if and only if P divides AB implies P divides A or P divides B. So if I can start off with P divides AB and then get to P divides A or P divides B, then I will have shown P is prime. So what we're going to do, we're going to assume here P divides AB. So let's assume, or let's say suppose P divides A times B. So if we're able to show P divides A or P divides B, then we will have shown P is prime. So we need to figure that out from the green that's given. Well, remember here in green, we basically have two cases. Case 1 is the GCD of A and P is 1. Case 2 is P divides A. So I'm going to do a case 1 and a case 2. Case 1. Let's suppose the GCD of A and P is 1. Okay. Now let's go back to theorem 1.4. Theorem 1.4. And that was the generalization of Euclid's lemma. So if P divides AB and the GCD of P and A is 1, then that means by theorem 1.4, P divides B. That's sometimes called the generalization of Euclid's lemma. Okay, so we've shown P divides B. The other thing we would show is or P divides A, so that would be case 2. So we'll do case 2. Suppose P divides A. That would be this right here. Well, there's nothing to show. There's nothing to show. So what do we have? We have either P divides B in case 1, or case 2, P divides A. So if P divides B or P divides A, then by Euclid's lemma, that's theorem 1.5, then P is prime. And that's what we wanted to show, P is prime. So again, the proof. We had a forward direction and a backwards direction. Pretty nice little problem. Okay, I'll throw another one in here. This will not be exercise. This will be from your book, Corollary 1.6. Remember what a corollary is. A corollary is basically a mathematical statement that follows from another statement. Now this is going to follow from theorem 1.5, which was Euclid Sum. It says if P is prime and P divides a long product, A1, A2, and so on. Well, let's say A3 through AN. So let's say P divides a long product of factors. Then P must divide one of the single factors. Then P divides, we'll say A sub I for some I. So if P divides a product of factors, then P has to divide at least one of the factors. Let's go ahead and prove that. So we're proving an if-then statement, so let's assume that if here, that changed on me. Suppose P is prime, and P divides a product of numbers. Well, we can use Euclid's lemma, right? Since P is prime, by Euclid's lemma, so let's think about A1 as the A, and the rest of the stuff I'm doing here in red, A2, A3, AN, let's think about that as the B. So by Euclid's lemma, P has to divide A1, or P has to divide the red stuff, A2, A3, AN. And the triple dots, they should go in the middle. They shouldn't go on the ground. They should go in the middle of the screen. Okay. So then apply Euclid's lemma again. So let's call A3 ... AN. Let's call that the B this time. So A2 is going to act like A, and the yellow is going to act like the B. So by Euclid's lemma again, so we start off with P must divide A1, or applying Euclid's lemma again, P must divide A2, or P must divide the yellow, A3 through AN, multiplied together. So if I repeatedly use this Euclid's lemma by iteratively using Euclid's lemma, notice what's happening. I'm getting P divides the first term every time that I peel off. By iteratively using Euclid's lemma, I get P divides A1, or P divides A2, or P divides A3, ... or P divides AN. So you can do this for as many terms as you want. So thus, P must divide at least one of those factors, AI. P must divide AI for some I. And that's it. So we've proven it. All right, I think I will stop there.